Welcome back to AI.Code.Cast. You know how we do it, right? It's time for that daily coding challenge.
That's right.
And today, we're diving into a problem that's all about maximizing integers
Okay.
within certain constraints.
Sounds a bit abstract.
Yeah, it does a little bit abstract, right?
Yeah.
So,
That's why we're here, though.
yeah, exactly.
We'll break it down.
Break it down.
Imagine you're given a range of numbers, but some are off limits. Let's call them band numbers.
Okay.
Your mission, should you choose to accept it, is to pick as many numbers as possible from the allowed ones.
Okay.
But his total can't exceed a specific limit, which we'll call maximum.
Okay, so I'm starting to see the puzzle pieces here.
Yes.
It's like we're building the tallest tower possible
Uh-huh.
using only specific bricks, but some of those bricks are cracked and can't be used.
Exactly.
Right.
The challenge lies in figuring out how to choose the right combination of good numbers to reach the highest total without going over that maximum sum. It's a classic optimization problem that pops up in various coding scenarios.
So where do we even begin?
Right.
If I were to just start randomly picking numbers, it feels like I'd just be stumbling around in the dark.
Yeah, you're right. That wouldn't be very efficient.
Yeah.
In fact, that's the brute force approach, just trying every single combination of numbers to see which one yields the highest sum within the limit.
Oh, yeah. I can already sense the problem with that.
Yeah.
Trying every single combination.
Oh, yeah.
It would take forever, especially if we have a large range of numbers.
Mm-hmm.
Talk about a computational nightmare.
Precisely, brute force might work for very small data sets, but it quickly becomes unfeasible as the problem scales up.
Right.
We need a smarter, more targeted approach.
I'm all ears.
Okay.
What kind of strategies can we use to streamline this process? I'm guessing sorting the numbers might be a good first step.
Sorting is definitely a valuable tool in our arsenal,
Okay.
but it's only part of the solution. We need to think about how to efficiently check if a number is banned. Make sure we're not exceeding that max sum along the way.
So sorting helps us organize the chaos.
Yeah.
But we need additional techniques to navigate those band numbers and the sum limit.
Right.
It sounds like we need to bring in some heavy-duty algorithms.
Absolutely. There are a few powerful approaches we can explore, each with its own strengths and trade-offs.
Okay.
Let's start with an algorithm that's well-suited for searching through sorted data, binary search.
Binary search. That rings a bell.
Yeah.
It's like looking for a word in a dictionary, right?
Mm-hmm.
You don't check every single word. You keep having the search space based on alphabetical order.
Right.
But how does that apply to our band number situation?
Great question. Imagine our band numbers are like words in a dictionary, all neatly sorted in order.
Okay.
Now, instead of searching for a specific word, we're checking if a given number exists within that sorted list of band numbers.
So we wouldn't have to check every single band number one by
Okay.
one. We could essentially eliminate half of the possibilities with each step.
Yeah,
That sounds promising.
exactly. Binary search allows us to zoom in on whether a number is banned or not with remarkable efficiency, especially when dealing with a large set of band numbers.
Okay, that makes sense.
Yeah.
So once we use binary search to figure out if a number is allowed, we then decide whether to add it to our running total, making sure we don't go over the max sum.
You got it, but there's a crucial detail here. The order in which we pick the allowed numbers can greatly impact our final result.
Ooh, interesting.
Yeah.
So it's not just about finding the good numbers.
Right.
It's about picking them in a strategic order
Yeah.
to maximize our chances of reaching the highest possible sum within the limit.
Exactly.
Okay.
And that brings us to an important question. What strategy should we use to select the numbers? Should we go for the largest ones first or start with the smaller ones?
I'm instinctively drawn to picking the largest numbers first.
Yeah.
Feels like that would get us closer to the max sum more quickly. But is that always the best approach?
That's a common misconception. Let's delve into why that might not be the most efficient strategy in this particular scenario.
Okay, so we're back to this idea of picking the numbers in the right order.
Right?
It seems counterintuitive, but you're suggesting that starting with the largest numbers might not always be the best way to maximize our sum.
That's right. Think of it this way. If we pick a large number early on, it might prevent us from picking several smaller numbers later, even if their combined total would have been greater.
Okay, I'm starting to see the light. It's like trying to fit suitcases into a car trunk. If you cram in a huge suitcase first, you might not have enough space for several smaller bags that could have fit in perfectly.
That's a great analogy.
Yeah.
So instead of aiming for the biggest numbers first, we should consider prioritizing the smaller ones. This way, we increase our chances of fitting more numbers within that maximum constraint, potentially reaching a higher total overall.
It's making a lot of sense. So we've got this two-pronged strategy. First, we use binary search to efficiently identify the allowed numbers.
Right.
And then we pick those numbers in ascending order to maximize our chances of reaching the highest sum within the limit.
Exactly. It's a beautiful combination of efficient searching and strategic selection. But let's not forget about the computational cost of sorting, especially with that initial sorting step in binary search.
Right, sorting does add some overhead, especially if our list of banned numbers is massive. Is there a way we could avoid sorting altogether and still achieve efficient lookups for those banned numbers?
There is. And this is where another powerful data structure comes into play, the hash set.
Hash set. Now that sounds familiar.
Yeah.
It's like a super fast lookup table, right?
Right.
We store our banned numbers in the special set, and then checking if a number is banned becomes practically instantaneous.
You got it. The beauty of a hash set is that it offers near constant time lookups. Imagine being able to instantly check if a number is banned without having to search through a long list.
That's amazing.
Yeah.
It's like having a magic detector for banned numbers. So with the hash set approach, we can skip the sorting step entirely and still achieve those blazing fast lookups.
Precisely. This makes hash sets particularly appealing when dealing with large data sets where sorting might become computationally expensive.
Okay, so hash sets offer speed, but there must be a trade-off somewhere. There's no such thing as a free lunch in the world of algorithms, right?
You're absolutely right. While hash sets excel at speed, they do come with a cost memory usage. The larger the hash set, the more memory it consumes.
That classic trade-off again, speed versus memory. So if we're dealing with a massive number of banned numbers, the hash set could become a bit of a memory hog.
That's a valid concern. We need to carefully consider the size of our data set and the available memory before opting for a hash set.
All right, so we've got binary search, which leverages sorting for efficient lookups,
Right.
and hash sets, which trade memory for speed. Both approaches have their strengths and weaknesses. Is there another way we could tackle this problem, perhaps a more visual approach?
There is. Let's shift gears and explore a technique called the sweep line algorithm. Imagine a line sweeping across the numbers from 1 to n, kind of like a scanner. As this line moves, it effortlessly picks up the valid numbers and skips over any banned ones.
I love that visual. It's like a smart vacuum cleaner, picking up all the good stuff and ignoring the dirt. But how does this sweeping line actually work? How do we know which numbers to pick up and which ones to skip without checking each one individually?
That's where the magic of sorting comes into play again. We sort both our numbers from 1 to n and the banned list.
Wait a second, we're sorting the numbers from 1 to n, but aren't they already in order?
Technically, yes, but thinking about it as sorting helps us visualize the process alongside the sorted banned list. Picture two lines moving synchronously, one across our number sequence and the other across the banned list.
Okay, I'm starting to see the picture. So as these lines move, we compare the current number on each line, right?
Precisely. If the numbers match, it means we've hit a banned number, so we simply advance the banned list line to the next number and continue comparing.
And if the numbers don't match?
That's our signal that the current number is valid. We pick it up, add it to our sum, and advance both lines to the next number.
So it's like we're merging those two sorted lists, our numbers and the banned numbers, and making decisions based on the comparisons. This sounds incredibly efficient.
It is. The sweep line technique helps us avoid unnecessary comparisons and allows us to add valid numbers to our sum very smoothly.
Okay, I'm really digging this sweep line approach. It's such an elegant and intuitive way to visualize the solution. But like any algorithm, it must have its limitations, right?
You're sharp. The sweep line technique heavily relies on the data being sorted. If the input isn't already sorted, we'll need to sort it first, which adds extra time to our overall process.
So it's a speed demon on sorted tracks, but might stumble on unsorted terrain. That makes sense. So we've explored three distinct approaches: binary search, hash sets, and the sweep line technique. It's like we've assembled a toolkit full of powerful algorithms. But how do we know which tool to reach for when faced with this type of coding challenge?
That's the million-dollar question, and it's what we'll tackle in the final part of our deep dive. Get ready to make some strategic decisions.
Welcome back to AI.Code.Cast. So we've explored these three different approaches
Yes.
to tackle our integer maximization problem, binary search hash sets, and the sweep line technique.
Right.
It feels like we've gathered this powerful team of algorithms,
Exactly.
each with its own strengths and weaknesses.
You're exactly right.
Yeah,
Now, the key question is, how do we choose the best approach for a given situation?
right. It's decision time.
Yeah.
We need a strategy to pick the right tool from our algorithmic toolbox.
Let's think about it like a flowchart. First, consider the size of our band numbers list. If it's relatively small, say a few hundred numbers, the overhead of sorting might not be a big deal.
So in that case, binary search could be a viable option,
Exactly.
even with that initial sorting step.
It offers that logarithmic search time, which is quite efficient, especially when we're not dealing with a massive amount of band numbers.
But what if the band numbers list is huge, like thousands or even millions of numbers?
Yeah,
Sorting that could take a significant amount of time.
right. In those cases, we need to shift our focus to approaches that avoid sorting altogether. That's where hash sets come into play.
Right, hash sets give us those near-instant lookups, regardless of the size
Yes.
of the band numbers list.
Uh-huh.
But we have to be mindful of their memory consumption,
Right.
especially with those massive data sets.
Exactly. So if memory is a major constraint, we might need to reconsider using hash sets, even if they offer those speed advantages. Now let's think about the sweep line technique.
Okay, the sweep line's elegant
Yes.
and efficient,
It is.
but it relies heavily on sorted data,
Right.
right?
Yes, and that's the key factor in deciding whether to use it. If our input data is already sorted, or if we can afford to sort it beforehand, the sweep line can be a fantastic choice.
Okay, so if sorting isn't a deal breaker, the sweep line steps in as a strong contender. It feels like this whole decision-making process comes down to a balance between the size of our data memory constraints and whether sorting is feasible or not.
You've nailed it. There's no one-size-fits-all solution in the world of algorithms. It's all about understanding the problem, analyzing the constraints, and then picking the right approach based on those factors.
This has been an insightful journey.
It has.
Through the world of algorithms, we've learned that it's not about declaring a winner,
Right.
but rather understanding the strengths and weaknesses of each approach and making strategic decisions based on the problem at hand.
And remember, the more you experiment with different algorithms, the better you'll become at navigating these choices. Keep practicing, keep exploring, and keep that algorithmic toolbox sharp.
That's a wrap for today's AI.Code.Cast. Until next time, happy coding, and may your algorithms always be efficient and elegant.